welcome for the afternoon talk. It's my pleasure to introduce Luc Brogat-Motte, who is a doctor currently doing a postdoc at Genoa, who is currently with Lorenzo Rotasco. And now Luc is going to present his previous work about stochastic differential equations.
Thank you, Florence. So yes, today I would like to present you a method to estimate control stochastic differential equation. So it's stochastic differential equation, but the coefficient takes as argument control input. So, and before going into the details, I would like to give a bit of motivation for this work. So why learning dynamical system and control dynamical system? Because first reason is because in real world applications there are many systems that evolve according some form of controls, but we don't know their dynamics. And so to give maybe a concrete example, we may not know the noise part, for example, of the dynamical system. So you can imagine, for example, a drone, but you don't know the wind, and so you don't have the full knowledge of the dynamic of the system. And one other example here is robots that try to manipulate a soft object. Here the dynamics is very complex. And so we may have some simulator for this derived from principle of physics, but it can be computationally expensive. And also we need to derive again for each deformable object the model for the system. So here the system, I consider it's both the robot and the soft object. Yes, and so why do we want model, an efficient model? It's because it's allowed to do many tasks. And I give some example. For instance, we may want to control the unknown system. We may want to make prediction or to optimize it in some sense. Also to do anomaly detection. And so to give a big picture of the challenge of this learning problem, the challenge are that we want, always in statistical learning, we want to efficiently estimate the system, meaning that when the number of data will increase, the accuracy will decrease the fastest as possible. And also the computational cost should not grow too much fast. And one challenge with this problem is that we have complex systems that are both stochastic and nonlinear. And also they are quite, they can be quite high dimensional in real world application. The state can be, of the system can be high dimensional, but also here, so this is an illustration of the problem I would like to tackle. We observe a stochastic dynamical system for a finished set of controls. Here there are 4 controls. And we, so notice that for one control, we have several trajectories because there are some kind of, there is noise. So for one control, you have a distribution of trajectory. You don't have just one trajectory. And the problem I want to tackle is for any new control, I want to be able to predict the whole probability distribution. Yes, exactly. And so it looks like a supervised learning problem, but as you can see, the input space, the input are controlled, so it's a function and can lie in very high dimensional space. So that's a challenge. Okay, so now let's define more mathematically the problem. Here's the outline of my presentation. I will start by defining the model and the learning problem we want to tackle. And then I will describe the method we proposed and the results we obtain, both theoretical and experimental. And theoretical, I mean learning guarantees. So the system, in this work, the system we control, the assumption we do, and is that the system is the solution of a stochastic differential equation with coefficients that depend on a control input. So here's an illustration. For example, for a fixed control, you start from a fixed distribution, which is already a kind of randomness. Then you have a different sample from this FD, and the noise also add randomness. And so our goal will be to estimate the map B and sigma that define this equation. B is called the drift component and is the one that can be thought of as deterministic in the sense that conditionally on the state it is deterministic. And sigma is the one that model the randomness. So for example, wind can be modeled with such equation. And to define such equation, I need to define Brownian motion and a space over which I filter probability space over which I define this Brownian motion. So this is the model for the dynamical system in this work. Now I define the density flow. So first we parameterize the family of possible controls. So we say that all controls that we consider are parameterized by theta in small theta in a big set theta, which is a compact subset of Rm. And then I define the density flow map. It's so for any control theta and for any time t, it gives the probability density of the system at time t under control u theta. So this is a picture of how this map looks like. For example, for this distribution, we have this density flow. So time increased from purple to yellow. Okay. So this is the first set of assumptions we do for this work. It's so the first one we do is that the noise is uniformly elliptic, meaning that it spans all the direction of the space. And the other one, we assume Sobolev regularity of the coefficient, of the parametrization, and of the starting density. And so all these assumptions can be thought of as we assume the system is smooth trajectory, smooth parametrization in the control. And so we limit our study to this kind of systems. It means there is not, so this comes from the uniformity. It means we don't have degenerated density. I mean, yeah.
Did you assume that for system is controllable?
No.
So it's possible to be X is not controllable. So if you come back to the original previous.
Yes.
So when sigma is equal to 0, do you have any assumption of controllability of B or no?
When sigma is 0?
Yeah. So is the M4 system controllable?
So here I assume it's greater than kappa identity, but it can be. But I don't do any controllability assumption in this work.
Yeah, this one.
Yeah, no, because.
So when sigma is equal to 0, the system can be anything.
When sigma is equal to 0?
Yeah, without noise.
Yes.
Are you assuming that the system is controllable, or
No, I don't assume. I don't need this. But okay. Okay, we can come back to it. So under this test of assumption, we have this well-Posnest result that just it's a theorem that just say that our system, there is so I define my system as a solution of SDE, and so the SDE doesn't have always a solution. But under my assumption of Sobolev regularity, I have a unique solution in this following sense of the system. So which is nice. And then I have also this result that mainly say, also under the same set of assumptions, that my density is well defined. So the flow is well defined. And I have another result, like a structural result on the density flow. It needs to follow this equation, which is called forward Kolmogorov or Fokker-Planck equation. So it's PDE on the density flow. And so it's with an operator L, which is defined above and which is explicit when you know the coefficient. And so this is the learning problem we wanted to solve. Given observation of trajectory, we want to estimate the coefficient of the SDE and to try to have guarantees on this quantity, which is a L2 norm over the space of control, theta, compact, over the time on a finite horizon, and over the state space. And we want to estimate it from trajectory data. So here, this set is, so I have K control, a finite set of controls. For each control, I draw n trajectories. And for all of these trajectories, I sample them at discrete times. And so here, it's illustrates well what kind of data we have. We have 4 controls here, so you can imagine it's our data set. We observe 3 trajectories for each control. And also we have, here it's not illustrated, but we sample the time, we sample discrete time. And we hope to estimate the density flow. In average, it should be accurate also for any control, another control, theta, which is in the parameter set. Yes. Yes. I will sample them randomly, ID on the compact set. Yes. Theta is the parameter of the control, so it's a parameter, yes, of a function. Yeah, I fixed it. I fixed a random. I fixed an initial measure. Yeah.
Is it the same for the different controls?
Yes. Yeah, like I'm starting randomly, but always with the same distribution. Mm-hmm. Yeah. Yeah, so A is sigma sigma transpose. So it's the. No, it's. Yeah, it was not clear. Yeah. So sigma yes is the diffusion coefficient, and A is the diffusion matrix. Yeah. Yes, I need it because I want to have a regular flow at the end. Okay. Okay, so now I will present the methods we proposed. So I add some assumption for learning. So it's the same set of assumptions but augmented. I assume that the so here I assume that the density flow is smooth. And the coefficient are smooth, as I said already. probably you could derive the smoothness of the flow of density from the smoothness of controls and coefficients, but it's not done, so I assume it's in this work. And I add the additional assumption that I have Boolean support of the coefficient. It means when the system exits a compact set, the coefficients become B become equal to 0 and A become equal to kappa E. It becomes like just driven by noise when it exits the set. Okay, so the key result we derived is the following one that I call the Fokker-Planck matching inequality. It says that for any coefficient in our hypothesis set, beta hat, a hat, the induced system will have distribution, will have density, which is L2 close to the true density. If the Fokker-Planck matching is small, because of we have this L2 norm is smaller than constant times the Fokker-Planck matching. And the Fokker-Planck matching is, so it's clear when you look at the expression of Fp, what I call Fp. When you take B hat, A hat equal to BA, it's equal to 0 because of the Fokker-Planck equation I mentioned before. So the idea is you have a P, which is the true one, and you know that it should verify this equation for the true coefficient. So you try to find coefficient that make this equation true. And it's justified because of this inequality. But we don't know P, of course, but it allows to break the problem in 2 steps. First, we estimate the density flow. And then, so here there is a typo, D is a big theta, sorry. And then we recover the coefficient from the density flow, thanks to the Fokker-Planck matching inequality. So now I will present the 2 steps, exactly the estimators that we considered. So what we do is for each control, we estimate the flow associated to each control observed. And to do so, I consider the kernel-based method. I consider a density estimator. And then to have the density flow, meaning the density at any time, I estimate it only at the observed time, and then I interpolate between all times with a kernel. So after this step, I have K density flow, one for each of the control. And then I solve this problem, which is the empirical version of the L2 problem that I already mentioned. So it's an empirical Fokker-Planck matching. I try to find coefficients that explain this in an intuitive way. I try to find coefficients that explain well the behavior for the K control that we observed. There is the technical ET. It's that so I can I assume that the coefficient was Sobolev with order big enough such that the Sobolev space is a reproducing K-line space, so I can use kernel. But also here I need to fit a coefficient A, which is a positive definite and greater than kappa identity. And so to enforce it, I propose 2 ways. A soft one, just you consider a finite set of points and you impose it. And a hard-shaped one, and I used a model, a kernel-based model that preserves the good properties of kernel models and ensure that the model outputs only positive definite matrix. And so we derive the following learning. Yes?
Statistical frameworks. You have many applications.
Yes.
Many. And what about the TIs? So you observe
yes, so
the solution of the SE over a period of time that is always the same.
Yes.
You have some uniform
Yes.
space.
There is two datasets. In fact, here it's the dataset I observe from my system, so typically from my robots. So for each control, I have a trajectory sample at time. And then I obtain a K function, which has the densities. And to do the matching, I can draw another dataset because I want this. The idea is I want an equation to be the equation to be true. I can. It's an equation that span the time and the space, and so I can draw I can draw time and position uniformly.
You have assumptions about the temporal mesh grid.
Here I just need to. The idea, so I have p hat in my Fokker-Planck instead of p, and then I need this to be small. I already sampled the controls, but I can resample the times here because I have function that I can evaluate for any time. And yeah, I have p hat k that take as argument t and x, and so I can sample times and space and evaluate this function, such that this is if I can evaluate this algorithm. Yeah. The R?
In the Gauss expression of the density, the slide before. The R is the bandwidth.
Yes.
You have a bias.
Yeah, I have a bias. Yeah. So I need to, when I did when I derive this the theoretical result, I need the first to compute the error between the pk hat and the true pk, and R play a role at this point. And then when I control this error, then I need to control the error of this step. But it needs to be chosen correctly to have a density that converges to the true density. And so we obtain this result, which says that so our objective is minimized by a constant times this rate. So the error goes to 0 at a polynomial rate in the number q, which is the number of data used for the second step. But I can, so of course it will become computationally extensive, but I can choose it. I can generate it, so it's not really a limitation. Here I think the interesting part is about K, meaning that I observe a system with a finite set of controls, and I want to generalize to all possible controls, and how the accuracy evolve when the number of controls are increasing. And so I obtain this polynomial rates, which are the standard rates obtained when you do kernel-ridge regression. You try to solve least square problems. You don't have noise, and you know that the function is in a Sobolev space, the true function, the true coefficient. And the interpretation is also the same. We have rates that depend on the smoothness nu of the system and the dimension over the dimension. And the idea is, so when the dimension increases, you can still have good rates, but you need to have a map that is smoother. So if not the case, there is nothing to do, but it's show that learning is possible even in high dimension if you have a high smoothness. We also wanted to derive stronger norm result in this work. And so there are two ones we consider. The first one is uniform guarantees. We wanted to have, so we didn't want to have average guarantees over the space of control, because typically in practice, what you want to say is you choose one control and you ensure that the accuracy of the of your estimated system is good, but not in average, because it's allowed to have some controls with very bad accuracy. And so we obtain this one, which are, so I obtain this rate, which are for a stronger norm, but I lose minus one in the right. So that's a bit the cost of trying to have guarantees for stronger norms. And also, Ricardo was very interesting in having CVAR guarantees, meaning that he wanted to ensure that the system, the tails of the system so if you have an observable F, which can be a cost, for example, he wanted to ensure that the tail of the system was correctly reproduced, which is important for risk, for application that are risk sensible. That was one optimization. So we obtained some rates, but I didn't put it there. And yes, so that's the takeaway message. We are not just accurate in average, but uniformly over the space of controls, also time. Yeah. And we faithfully capture rare, but possibly high impact events. So now I will show you some numerical experiments. I implemented the methods, and I started by implemented without control, or you can think about it in the limit case where you have one control. So it was a first step to evaluate the method. I consider this simple system, which is the system that I already showed you, but I will show you the results. And so here is the result of the method. So we observe these true trajectories from the true coefficient BA that I just showed you. And we estimate the density. This is an illustration of the estimated density. And from the density, we recover the coefficient that explain well, that should explain this density. And we obtain, so this is a sample simulated from estimated B hat and A hat. So the observation is the behavior of the system is approximately recovered, meaning the variance and the mean is correct. When time increased, the error increased because it's also, so I didn't quantify it in my result, but when I did the derivation, the accumulation of error can be seen in the computation. So that's why. And so I implemented also the control version. So where you sample a finite set of control, I consider this SDE, which is Orchen-Uhlenbeck SDE. So linear in the states and in the control. And the control here I consider only steps. And so the parametrization of the space is the height, the height of the steps, and also the time where the second step arrives. So there is 3 parameters. I sample 10 controls, and I sample 1,000 trajectories for each of the control, and the hope is to be accurate on any control of this space of control parameterized. And so I obtain this result in dimension 1. So here are 3 test controls, and below you have the true trajectories from the true coefficient and from this control, and then you have the simulated trajectories from the estimated coefficient for this controls. And so again, you can see that the dynamics is correctly reproduced. What is important is that the control here, I draw them randomly, so it's they are test control. They are not taken from the training set. So it's experimentally, it's generalized well to unseen control. Okay, so I will just to sum up this work. So it's a work about estimating a control stochastic differential equation. We propose the method with learning rates that are adaptive to the Sobolev order of the estimated system. And we also provide 2 open source Python libraries for this system that I try to document it well, so you can test it. I think it's user friendly, and so that's it for this contribution. And as future work, I see I'm interested in these three general problems. I already started to work on the first one. So because you have a system which is controlled, you can try to, instead of randomly picking the control, you can try to pick control that makes your system that allow to estimate faster your system by picking the control that makes your system goes in the area that you don't know well to have a faster rate. That's a work that we propose already a first method for this. Also, I would be interested in real-world experiments. So at IIT, there are many people that works with robots, and I think testing this method will be, for example, on the first example I show you of the robots which need to fold. I have a colleague that work on this problem, and I think having feedback from real-world system would be very interesting. And then the last important direction that I'm working on in IIT now is to estimate the system, but from a single trajectories. Because with this work, I need to resample the system from the same initial distribution, which can be in practice a limitation. And so I'm interested in trying to estimate the system only observing one trajectories, but the horizon increase, of course, and probably we will need to do some assumption like ergodicity to have a good coverage of the state space. Yeah, that's it. Yes?
Can you go back to the balance? Okay, so it seems that the rates first, you have lower bounds on it. Each term looks standard with
yes. Yeah.
Assumptions, but there is no interaction between the sampling time and the number of replications.
Mm-hmm.
And you could, if you have a global Sobolev assumption, maybe you could have interactions between, maybe there are some values for the control parameter that do not require
yes.
too many points to recover the drift and the relativity. So it's, are you sure that this is optimal?
No, actually, in the paper, so it's for the presentation. What I assume is so yeah. No, you mean assuming different Sobolev regularity for the time and for the.
Yes, but even the supremum here, this is really
the best. I don't know. What do you
the minimax sense? If you have a lower bound.
So the rate below, I think, is quite good. I think it's so it's the polynomial rate is the standard one, so I think it should be quite good. But what you are talking about is the first part. And for this, I don't know if I don't know. I'm not aware of like minimax bound for the density part, but I didn't really investigate this part. Yeah, surely.
add ergodicity will control the movement behavior.
Yes.
So you want to get some result.
Infinite time. Yes, infinite sample.
So you will get some results from a stationary distribution in that case?
Yes, exactly. And like assuming, for instance, geometric ergodicity to control the speed of convergence to the stationary distribution.
What would you need to expand it to elliptic you assume elasticity?
Yes.
If you would like to expand this to systems,
So I'm not sure, but would it mean that the density doesn't exist? You could.
you could work with stationary regime.
Yeah. Okay.
At least you could estimate the invariant density.
Mm-hmm. Ah, yes.
But do you use some X
No, I just needed to have. Sorry. Yes.
You can add density.
Yeah, I need to have density and. Okay, in this case also. Okay. Okay, yeah, that would be interesting. So it would allow to avoid this. Yeah.
Where you need this for density estimation.
Yeah, to have the to be sure. Okay. Yeah, sure.
Yeah, probably this is where you need the global comparability.
Mm-hmm.
So if you want to be hyperrealistic, you need the
Okay. That's okay. It's like.
This is what I see. But, yeah.
Okay.
But I still don't see why you are not using comparability. It should show up some. Maybe it's like hidden somewhere in the assumption, but it should show up somewhere.
I don't know well because in a sense here it's I don't assume any kind of assumption like controllability, but it's because I allow the system to restart. No, so it's like I can. I don't know. I don't need to know how the system will. I don't need to control it in a certain sense. I just need to span.
You're still trying to control by minimizing the yeah, we can discuss it later.
Yeah.
But
Yeah, we
can. It should show up somewhere. It cannot.
Okay.
It's probably hidden in your assumption.
Yeah. Maybe.
But I think the show up
Okay.
more explicitly to do with the.
Yeah, we can discuss it offline.
So 2 days ago we had a talk from a woman, and it was also based on this idea of gradient matching, that is a long,
Mm-hmm.
an idea that is used a lot in the deterministic case, reason function, and he showed us the two-step in jointly.
Mm-hmm.
Okay, so I know that to study statistical guarantee, it's convenient to
Mm-hmm.
two-step.
Yeah.
That you use the kernel density estimation. But did you thought about doing that simultaneously, maybe with another non-parametric estimator?
I know. Yeah,
So it's more involved in terms of optimization, but just learning simultaneously.
the two steps.
Yeah, two-step.
Like a one-step method.
Yeah, the one-step method, so that.
Yeah, that could be possible. Yeah, meaning we have bad approximation of the density at the beginning, but then. But the thing is that so there is no interaction. So we can learn the density increasing like this, but there is no interaction when the quality of the coefficient I estimate in step 2 does not affect the learning of the densities that are.
But the quality of the estimation of the density affects.
Yeah, completely. Yeah. in this.
You have considered applications. You mentioned anomaly detection and link
Mhm.
detection. Does it work numerically? You're able to detect something with
I don't know. No, I didn't test it, but yeah, it will be interesting application. Yeah. Mm-hmm. So it's in discussion. We have meetings with the more applied researcher at IIT, and it's a discussion between them and us to understand where it will be really relevant to try to test it. I don't. I think probably I would be interested in control. So typically in robotics, I would be interested in testing out on the robots that they have at the Italian Institute of Technology, and to see how well it can generalize on this true system. And probably there will be many questions that will show up when we'll try to implement it. That will be very informative, I think, about